Hello, everyone. Brian Gockel here with the Weather Service Office of Observations. Welcome to the Satellite Book Club Seminar Series. This is number 225. Today's presentation is the role of LEO observations in enhancing tropical cyclone prediction. Our presenter today is Dr. Isaac Moradi, research scientist from the Earth System Science Interdisciplinary Center. Our facilitator today is Chris Smith, GOES-R satellite liaison to the Ocean Prediction Center and the Weather Prediction Center. Just a few reminders, the session is being recorded, and per the OCIO Privacy Act guidelines, please keep your microphone muted and webcam off throughout the session. See the pinned message in the chat for more information. The Q&A section will be after the presentation as usual, and we encourage attendees to post their questions in the chat room, and they'll be fielded from there. If you are logged in under an alias account, please sign in with your full name or specify your full name when asking a question in the chat. Always looking for future presenters. Please contact the TowerS team if you're interested in facilitating. We put together a nice form. I'm going to be using that form pretty soon, so it's also in the chat there to sign up to be a presenter or a facilitator or otherwise participate in the book club. We welcome your involvement. In fact, we rely upon it and appreciate it. Training team can help develop training materials that may be as yet unavailable. Contact Ross Van Til for information questions about that. Thanks to the OCLO Learning Group, to the GEO and LEO programs, as well as other participants, and to our facilitator, Chris, today. Before we turn the mic over to Isaac, a few words about his background. Dr. Isaac Moradi is an experienced remote sensing scientist with nearly 2 decades of expertise in microwave and radar remote sensing, particularly in their applications for NWP. He's currently a senior research scientist at the Earth System Science Interdisciplinary Center at the University of Maryland, and he serves as the chair of the Data Assimilation and Numerical Modeling Working Group. His research focuses on advancing satellite data assimilation, microwave remote sensing, developing next-generation radiative transfer models, and integrating artificial intelligence and machine learning into numerical weather modeling. Isaac, welcome to the Satellite Book Club. The floor is yours.
All right, thank you very much. Let me just turn on the microphone. Hello everyone. I'm Isaac Moradi. I was introduced. Let me thank my co-authors. I think you know all of them: Satya and Vijay from NOAA, and Yanshu Zhu, formerly from NOAA, and now she's with NASA. So I'll be speaking about the role of LEO observations in enhancing tropical cyclone predictions, and I have a few bonus slides on the general role of LEO observations in day-to-day weather forecasts as well. So when it comes to tropical cyclones, I probably don't need to really tell much about the importance of predictions for tropical cyclones. They affect millions of people every year. They destruct our homes and take lives. So this was a study done 2022. They look at the death rate at the county level. So for each day, their conclusion is for each additional cyclone day per month, there is an increase in death rate in the following month due to injuries, 3.7%, infection, 1.8%, respiratory diseases, 1.3%, cardiovascular, 1-2%, and due to psychiatric reasons, 1-2%. So it's not really just a matter of hitting us and leaving us. The communities are affected by tropical cyclones for months and years after the cyclone passes. So there has been some really deadly tropical cyclones in the past, especially before the numerical weather predictions became common. So the deadliest one is the 1970 Bahawallah cyclone in Bangladesh. That the death rate was something close to 5 million people because of that cyclone. And there has been quite a few deadly cyclones in the US as well, the rate of 2,500 or so. So when it comes to weather predictions, accurate weather predictions, there are things that we can't really prevent. We can't redirect them, or cyclones are going to destroy homes, but the accurate predictions are going to give us time to prepare. So there is an example on the left. No matter how accurate the prediction is, it's going to be some damage. But if you really are prepared for the cyclone, there are a lot of damages that can be prevented. You see in this big cyclone, in this big circle, the homes that when the windows are covered, for example, you can save your home. The industry, they can prepare when they get the forecast in time. But there is one thing that we can't really do with accurate weather prediction for tropical cyclones, something that you can't really put a price on it, and that's saving lives. If you can't really predict them in 3 to 4 days ahead of time, they give enough time to evacuate people, and that's the most important aspect of the forecast for tropical cyclones. Well, they happen in quite different regions. So the U.S. East Coast is one of the regions that get hit by these cyclones quite often every year. So this is the frequency of occurrence for a period of 30 years for tropical cyclones, regardless of the intensity. And we are not the worst place in the world when it comes to tropical cyclones, but the U.S. East Coast, especially, is one of the, and Southeast, that really gets hit quite often. So when it comes to the numerical weather prediction, so this is a two-step process, and I'm pretty sure most people in this call, they are familiar, but just in case. So we get a first guess that comes really from the model previous forecast, and then we have the observations, many different sources, conventionals, LEO, and so on. We combine the first guess and observations through data assimilation process, and that produces something we call analysis. We use that in different ways to initialize the next forecast run. And that could be a long forecast, or it could be a short range forecast to provide the first guess. So when it comes to regional models, this first guess comes normally from the global models. Like, for example, for the HAFS model, the first guess and the initial and boundary conditions are provided by the UFS global workflow. But in global models, it's the model itself that provides the first guess as well. So millions of observations are assimilated into NWP models. This is, you see the time down here. This is the observations that are assimilated into the NASA GEOS model. So the LEO observations, you see them, those are the boxes that are moving, those are LEO observations. I hope you see my pointer. Then we have the aircraft, for example. We have a lot of ground-based here and there. And then the geostationaries, those are normally the sad winds. They just light up once in a while that you see them. So there are two different ways to look at the impact of observations in day-to-day weather forecasts. One of them is FSOI, forecast sensitivity to observation impacts. So the way it works, generally, you run two weather forecasts, one with the observations being assimilated in the initial conditions, and one without the observations being assimilated. And then you look at the differences between the two. There are mathematical ways to project the difference between the two to different observations. So this is something that is done using the NASA GEOS model, GMAO model. So on the x-axis, we have the fractional impact from observations. On the y-axis, we have different observation types. So radiations, they are really still important observations, because they are really the only observations that give us the profiles of temperature and humidity directly. And then we have all the satellite observations listed. For example, AMSU is microwave, ATMS is microwave, YASI is infrared. We have GPS-RO, and then we have AIRS, YASI, those are infrared. So the satellite observations by far are the most important observations that are assimilated into numerical weather prediction models. And of course, radio sound and observations are still a very important source of temperature and humidity profiles. So on the right, if you look at the observation impact per channel for the ATMS instrument, you see we are really just using a few channels from ATMS, 5 to 10, and the rest of them are underused for different reasons. For example, those 1 to 4 are sensitive to the surface too much. We have error in the emissivity modeling. 16 and above, they are sensitive to clouds, and we have problems with the forward modeling, so they are not used. So if we can really make better use of the observations, the satellite observation impact is going to be even higher than what I'm going to show here. So what we did, we look at something close to 10, 12 different tropical cyclones from 2017 to 2023. So it's not a single hurricane, because there are cases that you see a lot of the large impact from observations, and there are cases that you don't really see that much impact. So you should really look at the average impact that you see for a period of time. And running really these experiments for such a long period, so this is the work that has been done over a period of 5 years, really. So in the experiment that I have, so for looking at the impact on tropical cyclone analysis, I mentioned the FSOI. We have to use a different way, and that's really to remove the observations from the assimilation process and see how they impact the results. So what I have done, I have run 2 sets of experiments, 2 different model resolutions. One of them is C360. That's the research mode that we run at NASA, as well as the same at NOAA. These are lower resolution at 25 kilometers, and then there is a higher resolution at 12 kilometers, that's C720. So when I talk about all observations in the following slides, it means that all the observations, conventional GPS, RO, sat wind, as well as satellite observations, have been assimilated into the system. When I talk about conventional only, then it means really only aircraft and ground-based have been assimilated. So the models, the NOAA, what we call the forecast initiated by NHC, which are probably an ensemble of models, as well as the skills from the forecasters. Those are labeled as official OFCL. The AVNO are the forecasts from the NOAA global model. I have H4 in the following slides, the Navy global model, as well as the UKMO regional model. So here I have the track error on the left and max wind error on the right as a function of the forecast lead time for several models of OFCL, H4, AVNO, Navy, UKMO for the period of 2012 to 2024. So this is for a period of 12 years almost. So the track error, if you look at the track error, so the NOAA, what we call the official forecast, they are still the best really forecast for the North Atlantic region or basin. So they have the lowest track error. And then the UK Met Office forecasts are the forecasts that generally follow the NOAA official forecast. So then we have the global models. We have the H4, which is the regional model, as well as AVNO, or the global model as in the middle, and then the Navy has the largest error. So in terms of the max wind speed, the H4 and the NOAA forecast, they are among the best. And then the other 3 they have a larger error. So the NOAA, what is called really the NOAA official forecast, they are still the best forecast that being issued. So in terms of the experiments that I ran, so these experiments, on the left, I have the track error due to assimilating or removing observations from the process, and on the right, I'm more or less looking at the impact of model resolution. So in terms of the observation impact, so the red one is when all obs are assimilated, and the blue one is when only conventionals are assimilated. And you see when we add satellite observations on top of the conventional, then we see improvement in the track forecast. It could be something like after 2 days, for example, it's almost 100 kilometers. After 4 days, it's almost 200 kilometers. So on average, ranging from, let's say, 100 to a few hundred kilometers improvement when we assimilate satellite observations. So this is for an average for 5 different hurricanes. They are listed here: Irma, Humberto, Lorenzo, Jerry, and Dorian. So in terms of the model resolution on the right, I have read C360 all observations. So that's 25 kilometers. And then blue is 12 kilometers using the NASA GEOS model. So when we increase the model resolution, it improves the track forecast as well, but it's not as much as what you see from the observations. So that improvement is something close to 50 kilometers. This is only for 3 hurricanes. So I can't really run this C720 for a long period. So I just have it for fewer hurricanes compared to when I run at a low resolution C360. But overall, assimilating, increasing the model resolution improves the track as well, but it's not as much as when we add the LEO observation. And you see other models generally, they are very close. Still, if you look at the OFCL is still the best track prediction, followed by the UKMO. So when we go from C360 to C720, then the GEOS does really a nice job. It's very close to, for example, GFS that was running at even higher resolution than GEOS at the time. So this shows an example for a single case. This is Hurricane Jerry, September 18, 2019. So this shows what happens. So the black line is basically the track that, or the best track data that we have from the observations. And then we have other experiments. So if you compare the cyan and the blue one, when we assimilate all the observations, you see if we don't assimilate the observation, then this cyclone, the forecast showing it's really going right over those islands like Puerto Rico and other islands. But when we start to add other observations, like for example, con plus RO is the amber one, the next one, they start turning the storm towards the north. But when we add more observations, then it really gets closer, much closer to the actual track. So this shows what happens if you don't really assimilate observations. We are going to have some unnecessary evacuation, for example, in this case. So in terms of the intensity, so I have the sea level pressure and wind error. Left is sea level pressure. So these are for the lower resolution. So red is all obs and conv is when I only assimilate conventional data. So the observations don't really improve the intensity forecast that much. Pardon me. But again, the other, like for example, H4 and those regional models, they have the lower error in terms of sea level pressure compared to the low resolution experiments that I'm running. So on the right is the wind speed, the same thing. Satellite observations do not really contribute much in this case to improving the wind speed. This is at the sea level, but at the higher levels, they actually, I have a slide, they actually improve the vertical structure of wind and temperature anomaly that I'll show. But probably one of the reasons is, most of the satellite observations, we can't really assimilate them, the channels that get close to the surface because of the emissivity issues. So in terms of model resolution can really help to improve the intensity and wind speed error. So red is low resolution, blue is higher resolution, and you see something close to 15-20 hectopascal. And for the wind speed, we are talking about maybe 10-20 knots improvement when we go from a low resolution red to high resolution blue. And so GEOS, even it's a global model, it shows really a very good skill in predicting tropical cyclones. It does a better job even than GFS in this case in terms of the wind speed. So this is a case for Hurricane Dorian. So these are more individual experiments when I only add IR observations, or when I only add the microwave observations, or add RO observations on top of the conv. So the blue one is conv only. The cyan, the second one is conv plus RO. So RO, in some cases they improve the track, in some cases they don't really help. It's probably because of the the spatial resolution of the GPS RO observations is very low. They are not really very dense. But in some cases, they make some improvement in the track forecast. And then when we have all the observation assimilated. So whether you assimilate infrared or microwave, then the track improves a lot compared to when we only assimilate the conventional only. So because the SAD winds are from both LEO and GEO, and I wanted to remove the GEO from, you can say, okay, we have SAD winds, maybe they are playing a role, the GEO. So I removed the SAD winds. Sorry, I added the SAD winds on top of conventional here. So the blue is conventional only, and then the other one is the conventional plus SAD winds. So they don't really improve the track that much when you add them on top of the conventional. This is for one single hurricane barrel. If you run for other experiments, you might see something slightly different, but I just wanted to show this as well. So I mentioned even satellites, they don't really improve the intensity and wind speed for near the surface, but they improve the vertical structure. So there are two panels here. The left one, so these are the so this is the pressure, and what you see here, the shaded ones, the blue red, that's the wind speed, and then we have the temperature anomaly on top of it. So near the eye of tropical cyclones, we see higher temperatures, and that's because when the water vapor is lifted from the surface and then it condenses in the higher levels, it releases back the heat. So we see higher temperatures. So in terms of all ops, we see this clear vertical structure of the wind columns. The temperature anomaly reaches 6 Kelvin, but when you only have conventional, the eye hasn't been even really formed here. So it shows some important improvement in the vertical structure of the storms as well. On the right side, I have the difference between lower resolution and higher resolution. So this is for a different date. This is September 22nd, Hurricane Maria. So the higher resolution modeling is really important for the intensity and wind speed, as you see here when you compare this panel C720 with the C360. So we also look at how they improve the general day-to-day forecast. So this is the reduction in the forecast error for 2-meter temperature. So top left is after 3-hour lead time. So that's very close to initial condition. Then top right is 2 days after we initiated the forecast. Bottom left is 3 days, and bottom right is 5 days. So you see, so blue is good. It means we are actually reducing the forecast error. So this is also the difference between conventional and when we assimilate all observations. So overall for 2-meter temperature, we see about a Kelvin or so improvement over continental regions, and then over the southern region, Antarctica, we see a lot of improvement in terms of temperature. And you see the impact. In some regions, they are more sensitive to initial conditions, so the error accumulates if we don't assimilate observations. But there are regions that over time they really just tend towards the model climatology. So after like 3-4 days, the impacts go away. Of course, doesn't completely go away, but it reduces. So this is for 2-meter specific humidity. So again, the after 3 hours lead time, close to initial conditions, the satellites they improve a lot, the specific humidity and relative humidity, because they improve both the specific humidity and temperature humidity, and sorry, and temperature. So relative humidity should also be improved. And then after 2 days, we see there are regions more sensitive to initial conditions. The impact accumulates and so on after 3 days here. And then after 5 days, you see basically the blue, it means that adding satellite observations is reducing the forecast error. And this is for wind speed at 10 meter. Again, they are showing quite significant impact, especially over ocean and the southern region. So, there has been a lot of talk about using AI. This was generated by AI itself. And so whether we use a physics-based model or AI, the observations are not really going to go away. We are still going to need the observations, whether we are running an AI emulator or we are running a physics-based NWP model. So the impact of observations is not going to go away, even if we switch from physics-based to AI. So I mentioned just a few more slides, so we are doing other work to improve the assimilation of microwave observations in NWP models. One of the areas that needs to be improved is the forward modeling in all sky conditions, because CRTM assumes spherical shapes based on mean theory for all the hydrometeors, but in real world, the hydrometeors have different shapes. So we have used this discrete dipole approximation basically to generate realistic shapes for our scattering calculations. So here's an example of top. I have the ATMS observations. The bottom one are simulations done using the IFS, the ECMWF IFS profiles as input, and then using the old CRTM lookup tables for cloud scattering. You see there is a very large difference between the simulations and observations when we use the old lookup tables. But when we switch to using the new scattering tables that we have generated using DDA, we see a very good agreement between the observations on top and the simulations in the middle. So these are two different shapes. One is sector snowflake and one is large plate aggregate. But in either case, the simulations using the new scattering tables, they are much better in agreement with the observations. And we are also working on the assimilation of spaceport radar observations, such as the CloudSat CPR and GPM DPR, into NWP models, including NOAA, a global workflow. So the first step was to have a simulator, our forward model for the radar instruments on board a spaceport platform. So we have included this in CRTM now. You can simulate the radar reflectivity. This is an overpass from CloudSat over Hurricane Bill. So on the left top is the observations, and the bottom one are the simulations done using the new CRTM radar simulator. And we are moving to JEDI. So everything that I discussed here, the last few slides, they have been implemented in JEDI in both CRTM and UFO. We have modified IODA as well to be able to use observations from, for example, CloudSat CPR, GPM DPR, as well as Earthcare to be assimilated in the NWP models. Okay, the conclusion. So tropical cyclones, they really have, they cause widespread destructions every year. They impact millions of people. The accurate prediction is really going to help us to save lives, if nothing else. And that's something that we can't really put a price on it. Both microwave and infrared observations, they show they are important for improving the track predictions. The model resolution is more important for improving the intensity and wind speed. Even GEOS is a really global model. It shows a lot of skills in predicting tropical cyclone. That's really all. So I leave it. I give the control back to Chris. If I forgot to mention, I have a poem here that I want to read. Thanks to ChatGPT, I have no skill or talent in actually when it comes to something like this. Clouds swallow the sun with the storms, loud cry, winds and floods darken earth and the sky. But high above in the sky, so wide, LEO satellites track the storms right. Thank you.
Thank you, Isaac, and thanks for that poem there. I do encourage all attendees to please stay on for the discussion, including field forecast offices and regional headquarters. And I encourage everyone to change the meeting layout to tiled and select hide tiles without videos. I think Kishald's bringing that up now, if you'd like to see the speakers. I hope everyone can submit questions and indicate if you want to ask the question verbally. You can also do that and come off camera. So looking forward to next week. In a week from today, on Thursday, March 6th at noon Eastern, we'll have Joseph Patton from CSS discussing the examination of the May 30th, 2024 tornadic weather event over West Texas. If you have any questions, you can contact the Tower S team, Kishald Bowman and Emily Maddox, for questions about the Satellite Book Club or for configuration of satellite products. So I'll see if there are any questions in the chat and I can get us started. Isaac, I was curious with, the infrared sounders now making it on to some of the geostationary missions, if there's any plans to run experiments like with the Meteosat sounder that'll be coming in the next year or two. Do you have any intel onto that, or if you're excited, to look into some of the impacts from those observations?
Yeah, the new sounders, like we are looking, for example, on CubeSat sounders. So the new observations, as they become available, there is a process that we have to go through and do experiments offline to make sure that, there is a lot that you need to do before really doing the assimilation process. For example, preparing the observation bias correction files and preparing the observation error tables and so on. So it's a process that we normally work on and try to get the observations as soon as possible. And of course, there are people from EMC, they are also working on those, as well as from GMAO, continuously trying to get the new observations in the system.
All right, thank you. And I saw, coming from the Ocean Prediction Center, we look at scatterometers a lot. I know that those had some minimal impact on the actual predictions of intensity. I was wondering if any higher resolution ocean-derived winds data sets would have a bigger impact, like synthetic aperture radar, where you go from 12.5 kilometer with scatterometers to 500 meter resolution. I know that's kind of leading into the future, but I just think it would be interesting to look at that as well. I didn't know if there were any plans for that.
Yeah, so higher resolution observations are always good, but on the other hand, we also need to improve our model resolution. Like if you run, let's say your model has 5 kilometer resolution, your observation is as 500 meter, you really are having a mismatch between your observations and the model. So you generally have to do some spatial averaging to have the match. Or if your observation is at much lower resolution, again, so generally this, I believe, like trying to match the observation and model, that's one thing that we always have to do. But high resolution observations are always better, and we are not really making best use of the observations. I show for ATMS, for example. ATMS is an instrument that has a lot of capabilities for clouds, hydrometeors, snow precipitation, but because of some of the problems in our forward model, or the NWP models are not able to give us the right clouds, right vertical structure of clouds at the right time and right place, we are not we are not using all the channels from ATMS, for example.
All right, I appreciate that. And I was curious, as helping support operations, looking at some of these microwave channels in real time. Do you have a couple recommended channels to look at the precipitation structure for tropical cyclones or extratropical cyclones from ATMS, for example?
Yeah, those channels for ATMS, new scattering tables that I just shared, so you can now assimilate the channels that are 16 and above. Those are channels sensitive to snow and frozen hydrometeors, as well as the first 3 channels that we haven't really been using. Those are sensitive more to rain and liquid clouds. So with the new tables that I mentioned, these are in CRTM already, in CRTM version 3. And I'm actually working with different people from NOAA and NASA to make use of the new scattering tables that we have in CRTM that should help to use the channels that are sensitive to rain and snow, for example. Thank you for that question.
Yeah, thanks for that answer. You did have an interesting slide. I think it was a January 2023 analysis showing the different observations and instruments on the left and on the right with the 22 ATMS channels. Can you briefly explain why AMSU has more impact than ATMS? Is it because there were more operational AMSU instruments in orbit, or maybe at the time the NOAA 21 ATMS was rather new and not included in the analysis? Do you have any insight onto that slide?
Yeah, it's probably, so there are 2 factors. Like you mentioned, we have more AMSUs basically than ATMS. There was only 1 ATMS, so that's one thing. AMSU has been around for a much longer period than ATMS. And that's another thing, you know, the more you play with these instruments and their observations and errors, you can make better use of them. For example, for a long time, we couldn't really make much use of the CRIS observations. Even we knew that CRIS observations are great. So it took quite a few years for the NWP centers to make really good use of the CRIS observations. And then it comes really to, there is another thing, you know, if you have 2 instruments running right behind each other with 1 hour difference, it's most likely, you know, if your instruments are apart in terms of time and coordinates, they normally have a much better impact than if you have 2 instruments running behind each other, for example. So there are really different factors playing in the chart that I show. But overall, microwave observations, they show all of them are showing really high impact for day-to-day forecasts as well.
All right, thank you. And one more question we had was, some polar satellite data is pipelined from direct readout antennas in remote regions to ENSO, Central Operations for NWP model assimilation. And data from the direct readout antennas often arrives at ENSO earlier than stored mission polar satellite data arriving from McMurdo. Can you comment on the importance of low latency delivery of polar satellite data to NWP?
Yeah, so we used to run 3D VAR models. You know, it was a 6-hour period. You run the model, you take, you know, it was a period that you had to wait and then run the model. But with the 4D VAR, the sooner we can get the observations, really the better, because now we have the time domain. So if we can get the observations as soon as possible, that's going to be a lot more helpful with the 4D VAR system that both NOAA and NASA are running now, because you actually are having the time domain. So you don't, you know, we used to accumulate observations over a time window in 3D VAR, but we don't have to do that, or that time window is a lot shorter in a 4D VAR. So it's really important to get the observations in a timely fashion.
All right, thank you for that insight. Looks like we're running up to the end of time. So if there are no other questions here in the chat, I will turn it back to Brian for final remarks. Thank you.
All right, Chris, thanks so much for your facilitation. And Isaac, thanks so much for this brief. It's really great to see the satellite data impact on the NWP models for applications, including tropical. So we really appreciate you coming to us with this presentation. As Chris mentioned, please join us a week from now for Joseph Patton's brief on, he's got a tornado case in West Texas. I think it's in May 2024. And we saw Joseph was on the call earlier. Maybe he still is on. Joseph, we're looking forward to that. So y'all come back to join us for that talk a week from today. And with that, we'll wrap up today's Satellite Book Club seminar series, and we'll shut down the call and look forward to seeing you next week. Thank you.
Yeah. Thank you, everyone.